This is 4.8, part 3, and we're going to look at example number 4. Find the antiderivatives of simple compositions, the integration of the function kx dx. Okay, on the bottom of page 2, you will see all the kx formulas. So all this means is k is standing for a constant, okay? So k is a constant. So if we look at A, we have the integration of cosecant 5x cotangent 5x dx. So I see that this is in the form of kx. So there's a couple questions. The first question is, do we have a formula that has this particular product of cosecant times cotangent? And the answer is yes, we do. So the rule says if we integrate cosecant of kx times cotangent of kx dx, we will get negative cosecant kx all over k plus c. Okay? So whenever you have a value in front of x, and it's not just x, you have to use this particular rule. So let's go ahead and apply this rule. We know that cosine of 5x times cotangent of 5x, if I integrate that, I'm going to get negative cosecant of 5x. Now I have to divide by that constant k, which is 5, and then I have to tack on c. So if I want to write this up a little bit nicer, I could say this is negative 1/5 cosecant of 5x plus c, and that's my answer. Okay. All right, so let's look at B. B has two instances where we have kx's. So there is a rule for both of these. So the rule that hits e to the kx, so if we integrate e to the kx, if we integrate it, it becomes e to the kx over k plus c. And integration of sine of kx, and I should have wrote dx after that first one as well, but if we integrate that, we're going to get negative cosine of kx over k plus c. Okay, so let's go ahead and use these rules for B. Those were not appropriate for A, but they're appropriate for B. So if I use the first rule, e to the kx, the integration of e to the 2x plus the integration of sine to the 1/3 x dx, we're going to integrate that, so it's going to be e to the 2x over 2, because once again you take that constant and divide by it, plus the integration of sine to the 1/3 x is going to be negative cosine of the 1/3 x all over 1/3 plus c. Okay? All right, so let's clean this up so it looks a little bit better. I'm going to do 1/2 e to the 2x and then minus 3, because when you flip over 1/3 you get 3 cosine of the 1/3 x plus c. Okay? All right, let's look at part C. Part C has 1 over 1 plus 4x squared. Now listen, if I look up the rules, it doesn't really look right to me, right? But we can rewrite this so it does look like one of the rules. So if I rewrite it, I can rewrite this as the integration of 1 over and 1 plus, and I notice that 4x squared is a perfect square. So 4 is a perfect square because it's 2 times 2. And x is a perfect square because it's x times x. So if I rewrite it like that, now I can look up to see that I have a rule that looks like that. My rule states that if I have the integration of 1 over 1 plus kx squared dx, it's going to equal inverse tangent of kx over k plus c. Okay, so we're going to use this rule here. So once again, if I integrate 1 over 1 plus 2x squared, I know that's inverse tangent of 2x, because that's what kx is. I'm going to divide it by that constant 2, and then I'm going to add c to it. So if I rewrite it a little nicer, I have 1/2 inverse tangent of 2x plus c. So once again, all of these examples show you what we do with kx. Okay, let's look at d. And d is tricky because I do not have a rule for that, sine x. What I can do, though, is I could use a couple of different things. I can use power reducing formulas to try to figure this one out. And I'm going to write these on the side. These are very important. You will need them for Calc 2, okay? So for Calc 2, the power reducing formulas. Okay, so I don't know if you guys remember or not from trigonometry, but there was a rule that says cosine squared theta equals 1 plus cosine of 2 theta all over 2. Okay, so we can rewrite that as 1/2. If we factor out the 1/2, we're left with 1 plus cosine of the double angle. Okay, so that's one of the power reducing formulas. The second one deals with sine squared theta. So the power reducing formula says if sine squared theta is equivalent to 1 minus cosine of the double angle all over 2. And once again, I can factor out the 1/2. And when I do, I'm left with 1 minus cosine of the double angle. Okay? So for this particular problem, we are going to use the power reducing formula for sine squared. So I'm going to rewrite this up as 1/2 times 1 minus cosine of the double angle, or 2x in this case, dx. Okay, so I'm going to pop out the 1/2, and I'm going to integrate the 1 in terms of x, and then I'm going to put minus the integration of cosine of the double angle dx. Okay, now I have rules for both of these. If you guys remember correctly, the integration of 1 is rule 1, so I'm going to use rule number 1 on that. And rule 1 says if I integrate 1, I get x. So this first piece is going to be 1/2 x. Okay? And by the way, because I factored out the 1/2, I should have a 1/2 in front of the cosine as well. So that was just overlooked because, listen, we have to distribute it to both. Okay? So that's why the 1/2 got taken out there. So I'm going to keep the 1/2 out because it got factored out as a constant. And now I'm going to apply the kx rule, which we just saw earlier. But I guess I'll put it down here just so you're clear. So the integration of cosine of kx dx equals sine of kx over k plus c. Okay, so we're going to go ahead and do that. So this will be sine of 2x, and it's over 2, and then plus c. So making this look a little bit better, I'm going to do 1/2 x minus 1/4, because 2 times 2 is 4, sine of 2x plus c. Okay? All right. So that's using the rules and using the power reducing formula. So once again, if you see something that doesn't look like a rule, ask yourself, hey, can I rewrite this? Can I use algebra? Can I use trig? Can I use the power reducing formulas? Okay? All right, let's look at the next page, which is page number 7. So the inverse nature of derivatives and antiderivatives, we're going to be talking about that next. So if I take the derivative of the antiderivative, I will get the original function back. That's what rule number 1 is saying. And if I take the derivative of the antiderivative dx, I get the function plus c. And I also can integrate the derivative, and if I do that, I get the function plus c. So in general, the antiderivative of the derivative of a function will give you the original function, okay, plus c. All right, can't forget the plus c, okay? So now we're going to look at a little bit of something a little tiny bit different, solving differential equations and initial value problems. So if you have a differential equation and it says given dy dx equals the derivative of the function at x, and we have to solve for y equals f of x, all we have to take is integrate the derivative and we'll get the original function back. This gives you a general solution to the differential equation, which gives you infinite solutions. And the reason why they're saying that is because you're going to get some answer and you're going to get plus c. So remember that c stands for a whole family of constants, right? So for example number 5, it says given the derivative f prime of x equals 2x, find the original function. Okay, so what we're going to do to find the original function is we're going to take and integrate the derivative. Okay, so if we do that, we're going to integrate 2x dx. So I'm going to pop the 2 out and I'm going to integrate x dx. And by the way, I'm using rule number 3. So I get 2 times x to the first plus 1 all over 1 plus 1. So this becomes 2 times x squared over 2. The 2's will cancel each other out, and I'm left with x squared plus c. Okay, so that is the original function. So the original function gives me a whole family of values. So x squared plus some constant. Okay, so that brings us to the initial value problems. So the initial value problems, they're going to say dy dx equals the derivative at x and the initial value of the original function at x sub aught. And that's going to equal y sub aught. So we're going to solve for y equals f of x. So basically, all we're doing is we're going to be able to figure out what is c. Okay, and that'll give you an exact formula instead of a whole family of formulas. Okay, so this gives you a specific solution to a differential equation. All right, so let's see this in action. So we have example number 6. With a given formula, find f at x, i.e. solve the initial value problem. So we have the same function again. We have to integrate the derivative. So if we integrate the derivative is 2x. So we already did this. Remember, I did this one just a minute ago using rule number 3. So if you use rule number 3, you're going to see that that's x squared plus c. Okay, that's what the function is. Okay, so we have now another step. So the first step is to find the original function. And now the second step is to plug in values to find the exact solution. Okay, so we know that when y at 1 equals 3, right? So I know that x is equal to 1 because they told us that. And I also know that y equals 3. Okay? So if I plug that in, I'm going to have to use this information to find C. Okay? So remember y, or f of x, equals x squared plus c. If I plug in the values, remember y equals 3 and x equals 1. Now I have to solve for c. Okay? So this becomes 3 equals 1 plus c. So c equals 2. Okay? So my formula is y equals x squared, and now instead of putting plus c, I know that c equals 2. So this is the exact value when x equals 1 and y equals 3. Okay, so that's what initial value means. So you find the generic formula with all the family solutions, then you plug in the values that are given to find the exact solution at that point. Okay? So if we look at B, we're going to do the same process. First of all, I'm looking at this derivative that they're giving me, and I'm going to rewrite it. So I'm going to rewrite the derivative of the function as 1/2 x to the negative 1/2 power. Okay? Because if I have to find what the original function is, remember I'm going to have to take and integrate the derivative. Okay? So if I integrate the derivative, I'm going to pop the 1/2 out because it's a constant, and I'm going to integrate x to the negative 1/2 dx. I'm going to use rule number 3 again. So this becomes 1/2 times x to the negative 1/2 plus 1 over negative 1/2 plus 1. So I get 1/2 times x to the 1/2, because 1/2 minus 1 is positive 1/2, over 1/2. Now I'm going to see that these 1/2s are going to cancel each other. So my generic formula is going to be x to the 1/2 plus c. So that's step 1. So f at x, or y, equals x to the 1/2 plus c. All right, next step is to find what c is. So 2, look for c. So I'm going to plug in my information. I know that x equals 4 because it says f at 4 equals 0, and I know that y equals 0. So I'm going to plug and play. So 0 equals, and I'm going to write x to the 1/2 as the square root of x so I can solve this. And instead of writing the square root of x, I'm actually going to put the square root of 4 because that's what x equals, and then plus c. So what do I get here? I get 0 equals 2 plus c, or c equals negative 2. So I go back into the derivative formula, which I'm going to underline here, and I'm going to put y equals the square root of x and then minus 2. That is the initial value when x equals 4 and y equals 0. Okay, so once again, find the family of the original function and then find c. Okay, so we'll look at this one, and then I'll stop the video and start a new one. So example number 7, solve the initial value problem. We have the derivative is given as cosecant squared theta minus sine theta. So the $1 million question with this one is, do we have rules for this? And we do. The rule for the integration of cosecant squared theta d theta, the rule states that that is cotangent and it's negative. Okay. And then we have the rule for sine as well, the integration of sine theta d theta. The rule states that that is going to give me cosine theta plus c. Okay, so those are the two rules that I'm going to apply with this one. So to find the initial value, remember I have to find the function. So to find the function, I have to take the integration of the derivative, which is given as dy d theta. And instead of x, I'm going to put theta in there because that is my independent variable. Okay, so I'm going to take the integration of cosecant squared theta d theta, and then I'm going to do minus the integration of sine theta d theta. I'm just breaking up the pieces so I'm able to do this. So this is going to equal negative cotangent theta, and then I have a negative 1 that's hanging out in front of sine theta, and the integration of sine theta is cosine theta, and then plus c. Okay? So this is my formula. So I can say the original formula is y equals negative cotangent theta minus cosine theta plus c. Okay? So I've done the first bit. Actually, guys, the integration of sine is negative cosine, so this is going to change this into a plus. So let me just fix that really quick. Okay, so next we have to look at this, and we got to find c. So find c. I know that theta equals pi over 4, and I also know that y is equal to 1. So I'm going to plug in this information. So 1 equals negative cotangent at pi over 4 plus cosine at pi over 4 plus c. Okay, so I'm solving for c. So cotangent of pi over 4 is radical 2. So this becomes negative radical 2. And then plus cosine is square root of 2 over 2 plus c. So now I have a bunch of stuff that I need to do here. So I'm going to get, and I apologize, cotangent of pi over 4 is not radical 2. It is 1. I just checked my work really quick. That works out a little bit better. So I got to get c by itself. So I'm going to do 1 plus 1 equals square root of 2 over 2 plus c. So this becomes 2, and then minus radical 2 over 2 equals c. So 2 minus radical 2 over 2 is what c equals. So my last step is to put the pieces together. So my original function, remember, was negative cotangent theta plus cosine theta, and then instead of putting plus c, I'm going to tack on that 2 minus radical 2 over 2. And that is my exact value for the function. Okay.